And we're back. So now we're going to talk about energy, in particular, how it relates to what we were just discussing in terms of enzymes and metabolism. But first, we have to do a little bit of a review of what you've already learned about energy from past things, past classes you've had. All right, energy. Energy is the capacity to cause change or move matter against an opposing force such as gravity. We're more interested in biological forms of energy here, rather than it being quite so physicsy, but the ideas, the concepts are still going to be the same. All right, we got two major forms of energy. We have potential energy, which is the energy that's stored based on the position of something. Something that's higher up is going to have more potential energy than something that's lower down. And this includes chemical energy, because the three-dimensional shape, the position, the physical components of the molecule are part of its potential energy. Right? And then kinetic energy is the energy associated with the movement of the object. So that can include movement of things, of molecules, and it can also include heat and light. We'll need both of those as well. All right, so here we can see both kinetic energy, the diver diving into the water, and potential energy in this diver, this swimmer, being up higher than the swimmers down here at the bottom. So higher potential energy because of position, and then kinetic energy because of the movement. We've already seen examples of kinetic and potential energy. I just didn't give them those terms yet, but these should look familiar to you. So kinetic energy is associated with movement of molecules. So anytime we're talking about passive transport or diffusion, that is because of the inherent kinetic energy of the molecules moving in solution through aquaporin or through the membrane itself. Whereas potential energy is related to the structure or location of these molecules, and the chemical energy in bonds is a great example of that. So ATP has a lot of potential energy, and we can use that potential energy here in active transport to run our sodium and potassium pump. So we can spend the ATP to pump the sodiums out and bring the potassiums in. So both of these have to do with how molecules move across the membrane. Both of them use energy, but the energy for diffusion is going to be kinetic energy, the passive energy of its movement, and then active transport is going to require potential energy. All right, more chemistry and physics terms that we get to review really quick. So thermodynamics. So thermodynamics has two major laws, and we need to follow these because we live in the world. The first law of thermodynamics is the energy cannot be created or destroyed. So energy is transformed or transferred from one situation to another. So in this case, we have this cheetah running really fast. It is losing energy to the environment through heat and through the chemical reactions that it's running. And it got that energy by consuming food. Same thing is going to be true for us, just a little bit less dramatic. All right, the second law of thermodynamics is that the universe is going to tend towards increasing entropy. Entropy is another word for disorder, which is another way of saying that no reaction is 100% efficient. So if we put in a set amount of energy, we can't quite get the results of 100% of that energy out. We're always going to lose a little bit of energy towards the disorder of the system. That might be towards heat, or it might be towards breaking things down into smaller molecules, making a more disordered world rather than a very ordered sugar molecule, for example. So how do we see this in what we're going to talk about, our biological systems? So we're going to see lots of energy transformations. Everything we're going to talk about for the next 2 weeks is basically transforming energy from one form to another. So we can transform chemical energy in the form of food to kinetic energy in the form of movement. That's what we see here, going from the ice cream cone to the kids riding their bikes around. And we can also transform energy from light, from sunlight, into chemical energy to help plants grow, to make sugars, or run photosynthesis. So basically, these are two different views of how we see energy transformations. We can see energy transformations through cellular respiration on the left and through photosynthesis on the right. And that's exactly what we're going to be discussing for the next couple of weeks, is how we can transform or move energy around in the biological world from one type of energy to another. All right, more vocabulary about energy transformations. So there are two types of energy transformations, and that refers to how they're using their energy. So a spontaneous process occurs without additional energy input. These reactions are exergonic, and they're generally catabolic, which means that they're generally breakdown reactions. Just because they're spontaneous doesn't mean they're fast. We'll talk about that in a little bit. But these do not require the input of additional energy. They may require kinetic energy. They may require the energy that's already present in those molecules, but we don't have to add more energy to those reactions to get them to go. A non-spontaneous process requires energy input to occur. That's endergonic. And these reactions are generally anabolic, generally building things up reactions. All right, so we can see examples of these down here at the bottom. Here we have some kids. One is knocking over her sibling's tower. He's not too thrilled about it. That never happened in your childhood, I'm sure. This is going to be a spontaneous exergonic and catabolic reaction. It's a breakdown reaction that happens because of a change in the position, basically. And it does not require the input of additional energy for that to go. The opposite of that would be one of these endergonic anabolic processes where this kid is putting a lot of time, effort, and energy into building that tower in the first place. All right, back to thermodynamics. So in order for these reactions to be spontaneous, they have to have a negative delta G, a negative change in free energy. So this is 4 different ways of basically saying exactly the same thing. Let's go back to our divers. Here we have the diver, the swimmer at the top of the diving board, lots of potential energy, and then spontaneous change in free energy where they leap off the diving board into the water. They are less stable here at the top and more stable when they get down into the water at the bottom. This is a negative delta G because the energy is decreasing in this reaction. And because of this change, they go from having greater potential energy to less potential energy. In addition, the diver is less stable at the top of the diving board and more stable when they get into the water. This correlates very nicely with what's going on in a chemical reaction. There is more potential energy in this larger biological molecule. It is also less stable. So with a decrease in delta G, the molecules become more stable, smaller molecules here, with less free energy, less ability to do work. At the same time, entropy is also increasing because there's more disorder in the system. Rather than the molecule being nicely organized in this larger form, there's more disorder in its decomposed form. All right, the delta G calculation is pretty simple and straightforward. Basically, to figure out the change in free energy, that's what delta G means. You subtract the starting state, where they are at the top, from the final state, where they are at the bottom. And so because the starting state is more energy, you're going to wind up with a negative delta G from this reaction. We can use this delta G to refer to what's going on with our reactions, both for cell respiration and for photosynthesis. So we got cell respiration here at the top, where we go from glucose to carbon dioxide. This is an exergonic reaction. Our reactants have more energy than the products. Therefore, the energy released is negative delta G. So this is a spontaneous reaction. Photosynthesis, on the other hand, we start with carbon dioxide as our reactants. We put in a whole bunch of energy and build our products of glucose. This requires the input of energy, or a positive delta G. That makes this an endergonic or a non-spontaneous reaction. Right? If you need to review those terms, go back and watch the last 2 minutes again really quick. But it's important to be able to keep track of whether a reaction is spontaneous or non-spontaneous and what that means for what's happening with the delta G. All right. First one is spontaneous. Second one is a non-spontaneous reaction. All right. Now let's zoom in a little bit on what happens inside of these reactions so that we can talk about activation energy. So all reactions, whether spontaneous or non-spontaneous, require a little bit of investment of energy. Just enough to start the whole thing, get it started. Like that little kid knocking down the block tower. She didn't have to work hard to knock it down. Just a little bit of energy, just a tiny tap on it, was enough to bring down that tower. That is the activation energy. Often in our biological systems, this activation energy comes in the form of thermal energy, or comes in the form of heat, just the natural kinetic movement of molecules in the first place. All right, another vocab word real quick, the transition state. The transition state is the most unstable or activated state once you reach that activation energy. You have to get through that transition state so that the reaction can proceed or the reaction can continue. Let me show you what I mean on a graph, because this might actually make it a little bit easier. All right, so here's our reactants. Let's think of this like cell respiration. We've got glucose here, and then our products, things like carbon dioxide and water from our breakdown reactions of cell respiration. The delta G is negative, as we just talked about, because we're releasing that energy for our reactions. But to get there, we can't just go straight down from reactants to products. We have to go through this little awkward phase first, called the transition state, which is our most unstable state before going all the way down to products. The energy difference between the reactants and the transition state is referred to as the activation energy. This transition state is our most difficult, awkward, uncomfortable position. And it happens because the bonds are in the middle of breaking, but they haven't quite broken yet. They're really unstable. Remember, higher free energy refers to less stability in our molecules. So the more unstable you are, the higher your energy is. The more stable you are, the lower your free energy is. Importantly, it's this activation energy here and the energy of the transition state that regulates the speed of the reactions. So the larger the activation energy, the harder it is to run this reaction and actually get from the reactants to the products. So this activation energy itself right here becomes very important in a minute. All right, let's look at this new, not nearly as pretty graph, and label it with the information that relates to what's going on in this particular reaction. So I've given you a little bit of information up here at the top. So under standard conditions, the reaction water, H2O, to hydrogen gas plus oxygen gas has a positive delta G. Positive delta G, what does that mean? Oh, that means it's going up. Okay. The reaction hydrogen gas plus oxygen gas to water has a negative delta G. Right? Negative means that it's going down, energy is being released. Okay, so now that we have that information, look at this diagram here, this graph of the enzymatics of the reaction, and let's label this with the reactants, the products, and everything that's happening here. Okay, first step, we need to look at positive and negative delta G. What do we have on this graph? Well, our reactants are higher energy than our products, so that means that our delta G, the difference between the energy of the reactants and the energy of the products, must be going down. So in this case, our delta G is negative. All right, so I've just labeled that there on the graph. All right, while I'm at it, I'm going to label the activation energy. The activation energy goes up to this peak right here, and so it's this difference, in this case, between the reactants and the transition state. So this is the EA, or our activation energy, energy of activation. All right, that leaves us with just our reactants and products to label. That means we got to go back and look at our information here in the question, I guess, and figure out whether we're dealing with a positive delta G or a negative delta G. Well, we already drew in our delta G, thankfully, so that is helpful. And that tells us that we know we have a negative delta G. Therefore, Therefore, hydrogen gas plus oxygen must be our reactants, and water must be our product. Does that make sense to you? I hope so. If not, definitely please ask. Review it if you need to, but if you're still confused, absolutely you should ask. And we can work through more examples of this in class. Okay. So anytime you're dealing with a biological system, you're going to be dealing with a metabolic pathway. And a metabolic pathway has lots and lots of these enzymatic reactions. So if you think of each of these water wheels as being one of the enzymatic reactions, like we talked about in this complicated metabolic pathway over here, that means that there's lots and lots of these little graphs, lots and lots of these for every metabolic pathway. And that's what regulates the speed and the ability of these reactions to move forward. All right, so a couple of review questions to see if you're on the same page and thinking about this. All right, so we got two graphs here. We've got A to B going through a couple intermediates. That's one metabolic pathway. And then on the right, we have C to D going through a couple of different intermediates on its way. All right, so which reaction, A to B or C to D, yields the most free energy? All right, so think about that, answer it in your video, and then we'll go over it. All right, so hopefully you noticed that the difference in delta G between A and B over here is bigger. They're both negative, but is bigger than the difference in this delta G between C and D. Delta G here is also negative, but it's smaller than the difference between A and B. That means that the A and B reaction is more spontaneous than the C to D reaction. All right, next question. Same graphs, but just because a reaction is spontaneous doesn't mean it's fast. Which reaction on here is going to go faster? All right, think about that for a second. Write it down, answer it, and we'll go over it. All right, so the speed of a reaction is related to the activation energy. Do you notice how the A to B reactions have quite large activation energies, while the C to D reactions have much smaller activation energies? That means that even though C to D is less spontaneous, this one will be faster. C to D will be faster. So this is where enzymes are going to come in. The job of an enzyme is to lower the energy of the transition state and stabilize the reaction. So as the enzyme binds to the substrates here in the active site, it helps to stabilize this reaction, and it helps to make the reaction go faster and go more smoothly. So here's the same reaction without the enzyme in red and with the enzyme in blue. And because of the stabilizing of the transition state, the activation energy drops but when the enzyme is present. That will dramatically speed up the reaction and make this whole reaction happen a lot faster. All right, so that's it. That's our entire purpose of an enzyme. So the job of an enzyme is to lower the activation energy. It can do that in a variety of ways. It can bring the molecules closer together so that that will help the bonds change and switch and rearrange. It allows you to achieve a transition state where the bonds are stretched, but because they're stabilized in that environment, then the energy of it is lower. They're like someone's helping them stretch rather than them having to stretch on their own. It can also help by changing the local environment. So sometimes the active sites inside of enzymes have different pHs. That can help the enzymatic reaction happen a little bit more easily as well. And then sometimes the enzyme is able to directly participate in the binding of the substrates, just temporarily, just to help it switch and move things around. It's required, the enzyme has to be regenerated in its perfect form in the end, so any binding would have to therefore be temporary. All right, so I hope that that was helpful in connecting how enzymes and energy are related and how they're connected into metabolic pathways. In the next really short video, we're going to talk about two important molecules that are key for the energy of biological pathways, ATP and NADH. But if you've got questions on any of the enzyme stuff we just talked about, please ask. Please don't hesitate to let me know. All right, see you soon. Bye.